Alright, we're going to talk about concepts and foundations of remote sensing. This is the week 2 lecture component of the remote sensing class this week. So when we talk about remote sensing, we're talking about the art and science of obtaining information from data that we acquired at a distance. Not things that we physically went and measured, but things that we picked up, calculated, inferred from a distance, from away from a satellite, an airplane, etc. How does this process work? Well, it's sort of like this. The sun shines in the sky, hits on the ground or the water or the whatever. Some passes through, some bounces off, some is absorbed, and some is reflected. In this whole process, it makes things look differently. Different colors, different combinations of wavelengths of electromagnetic energy. Some of these you can see. That's why if you look in a parking lot, some cars are red, some cars are green. It all has to do with what is absorbed and what is reflected. But there's a whole lot more electromagnetic energy than just what we can see. And we can have sensors that can detect any number of these things. They could be flying low, they could be flying high, they could be in a satellite in space. We could also be taking this information and simply making pictures, or we can storing the data digitally, and we can have some reference data that could be images that we work off of, or other ways that we interpret that information. But ultimately, we try to take that raw data that we collect and make something useful from it, some product. And then that product is what ultimately makes it to the users. So we're going to look at this a couple of different ways. The first thing we're going to talk about is why remote sensing. Well, the source of spatial information is important. It can be scale specific. You can have global, regional, or even local information. The other thing about it is it's objective, and it's consistent, and it's detailed. And these are traits that help us make decisions free of bias. Another thing that we do with remote sensing and why it's important is because of the historical record and change detection. Whether you're looking at things like urban growth or flooding, or historical pollution, at the end of the day, what we're really doing is looking at how things were, comparing them to how things are, and if we have good information, we can make good comparisons, and we can actually identify this change, and that allows us to form a historical record or to indicate when these changes are taking place. Apologize for the yawning. As soon as I slap this headset on and start talking, it seems like I automatically start yawning. So how is the remote sensing system? Well, generally it works basically like this. You have a source of energy, you have a target, a background, you have a pathway for the energy to travel, and some sensor that picks it up. Now, what are these sources? So the first thing we're going to do is talk about energy sources and radiation principles. Now, we're not going to go on some long physics tirade of trying to understand everything, but it basically goes like this. The speed of light is fixed, and we know what it is. And so light travels at a certain wavelength and a certain frequency. Now, the wavelength is the distance between the peaks, if you will. So from one high point in the wave to the next high point in the wave, that is the wavelength. The frequency is the number of peaks per unit of time. Now, since the speed of light is fixed, and we know that however far and however fast light travels, it's really only a product of how long it takes to get from one hump to the next and how far apart those humps are. relatively speaking. And so from that, we can sort of make some distinctions. When we talk about waves, we generally use micrometers. We also use descriptive terms to label specific regions within the electromagnetic spectrum where we find things. And we'll talk more about those specifically in a bit. So when we look at the electromagnetic spectrum, we're looking at the wavelength of the energy, starting all the way down here with the very, very, very short wavelength. That means that the distance from one peak to the next is not very much. Okay? And that would be things like cosmic rays. Coincidentally, they have to be moving really fast because speed, frequency, wavelength, they're all related. So if you make the wavelength number smaller, then the frequency number has to get larger. In other words, you have a lot more peaks in a given unit of time. We move up from cosmic rays to gamma rays to X-rays, up to ultraviolet. And then we have a tiny little band here in our scale that's colored in. That's visible light. Visible light can be broken down into basically three regions: the blue, the green, and the red. And that basically goes from 0.4 to 0.5, 0.5 to 0.6, and 0.6 to 0.7. That is the only part of the electromagnetic spectrum that we can see, for the most part. Next up would be the near infrared, the mid infrared, the thermal infrared. Now, I caveated my what you can see outside the visible range a little bit because sometimes you can see some of that thermal stuff. You ever looked across an area when it's really, really hot? You may not actually be seeing the thermal infrared, but you can see the impact of it and how it, when it's bouncing off of an object, how it sort of distorts the other stuff. So we'll go with you can only see in the visible, but we can appreciate and make notice of some of these other things as well a little bit. Moving on up, microwaves, television, and radios. So let's just take a look at both ends of the spectrum here a little bit. X-rays, middle left, microwave or TV, television, far right. Short wavelengths, high frequency, lower wavelength, or shorter wavelength, lower frequency. That means that when we get over here to the right, there's less energy in that wavelength than what there is on the left. There's the visible spectrum made a little bit larger. Another way of looking at it is like this. And this sort of goes from a nanometer to a kilometer. And you can see that how that as they get much, much longer, their frequency has to go down. So we see 0.4, 0.7. We see blue, we see green, and we see red. Solar energy covers a whole wide range of stuff: ultraviolet, visible, near infrared, and even thermal. Talk a little bit about some math here. The characteristics of electromagnetic spectrum most easily explained by wave theory. How it interacts with matter can be explained by the particle theory. Electromagnetic radiation is composed of discrete units called photons or quanta. The energy of a quanta is expressed by all this, and blah blah blah. Just wanted you just to appreciate how complex this actually is. We're not going to go into it though in any much more detail on this, other than know that electromagnetic energy, light, and other forms can be explained and expressed in lots of different ways. So if we take those equations that we were talking about earlier, Planck's constant and all these different things, and we can figure out that the energy of a quantum is inversely proportional to the wavelength. That means longer wavelength means lower energy. So just like I was saying on the previous slides, when you get out to like AM radio signals, they have a very, very long wavelength. They're also very, very weak. That's why the signals don't travel very far and they get easily blocked by objects. Now, the other problem with this is longer wavelengths are harder to sense and detect remotely. So if you're looking at something that potentially is absorbing or reflecting something in a very long wavelength, you have to look at a very, very large area in order to see these multiple peaks. Everything above absolute zero emits electromagnetic radiation. Now, having said that, terrestrial objects are very different than the sun in terms of the magnitude and spectrum of what they emit. The total energy emitted varies with temperature, and Wien's displacement laws is the reason why. Examples: as you heat an iron bar, it changes color, okay, because it gives off different types of energy, different types of electromagnetic radiation. And so when it starts giving off in the red at one temperature, as it gets hotter, it becomes lighter, more yellow, eventually almost white. There's a concept in remote sensing called a black body, and a black body is a perfect radiator. So what does that mean? It means not what you're thinking. Think of it as an energy battery. All right. In a black body, a perfect radiator means that 100% of what is absorbed is radiated back out. Let me say that again. It radiates 100% of all energy of incidence. The energy of incidence is the electromagnetic energy that reaches the surface of an object. So what electromagnetic energy comes in contact to a black body is absorbed and then radiated back. Alright. Just taking a look here at the different wavelengths and the spectral radiant excitance factors. Basically what you can see that the visible radiant energy band is right there, and we look at these different curves, different temperatures, and you can see that a black body radiation curve at Earth's temperature is that line down there at the bottom. But as we heat up, it shifts further and further and further towards a shorter wavelength, and thus has a greater excitance. So what does all this mean in remote sensing? Well, it means that we basically have two systems that we work with: active systems and passive systems. An active system, we supply the energy, or the electromagnetic energy, whatever you want to, how it depends on how you want to think about it, and we sense what is absorbed to reflected or reflected. In a passive system, it relies on some outside source of energy like the sun, and we literally measure what is absorbed or reflected. So active, we supply the energy; passive, we use the radiant sources that exist in nature. Path length. Okay. Whether we're talking about active or passive, all energy passes some distance through the atmosphere. That is what path length is. Now, depending on how far it travels and what parts of the atmosphere it travels through, and the sensor and the electromagnetic frequencies that you're measuring, it can have a varied effect, okay, on the information. The primary cause is atmospheric absorption and scattering. So while we like to think of the atmosphere as this clear thing or whatever, it's really not. And some of the things that are in the air, literally, will cause some of this electromagnetic energy to scatter. Other things in the air will absorb part of it. So let's talk about scattering specifically. There's a bunch of different kinds, and we're going to focus on three. Rayleigh scattering is the first one. It is an atmospheric interaction, and it is in inversely proportional to the fourth power of the wavelength, which means nothing to us, or at least not to me. The short wavelengths are the ones that are most affected. That means something. So if the short wavelengths are scattered more, think about the spectrum of light that we can see. Down at the low end, we have the blue, the green, and then in the upper end, the red. So if the short are more affected, the blue is what gets affected. Guess what happens? We see a blue sky. That's because the blue light in the electromagnetic energy that's coming to the Earth is scattered more by the atmosphere. Now at sunrise and sunset, we see some interesting things. We don't see so much the blue. We see reds and oranges. Why is that? Well, if you think at where we're at on the globe at sunrise and sunset, the amount of atmosphere that sunlight travels through, because we're just about moving out of the range of the sun, it's traveling through a lot more atmosphere. So the more it travels through, the larger the wavelength that becomes impacted. And so in addition to the blue, we start to see some scattering of the reds and oranges. Next, we'll talk about Mie scattering. It's mostly caused by water vapor and dust, and the longer wavelengths are primarily the ones that cause this effect. And it is significant in slightly overcast conditions. And the last one is something called non-selective scattering. And what happens is you have particles that cause scattering. Okay? When those particles are much larger than the wavelength, they just pretty much scatter everything. Clouds are a good example. They scatter the heck out of everything. And so when you scatter all the energy, what color is it? White. So that's why the clouds look white. In terms of absorption, the result in loss of energy to the atmosphere. That's what happens. As this stuff scatters, some of it is absorbed. When it hits these particles, some of it is absorbed. And this results in a loss of it. The most efficient absorbers of electromagnetic energy in our atmosphere: water vapor, CO2, ozone. Remote sensing systems that we use to collect data, they have to be aware of this. And here's why. You have to design a system that addresses this, and you have to find frequencies that are not impacted, or at least are not impacted as much by this. And so you have these major absorbers: water vapor, CO2, ozone, but they don't absorb everything necessarily. They absorb parts of the electromagnetic spectrum. So if we're going to utilize the electromagnetic spectrum to our advantage, we have to utilize parts of the spectrum that are not impacted by these super efficient absorbers. Oftentimes when this happens and we have this range of frequencies that these things don't absorb anything from, we call that an atmospheric window, because it's just like a window letting that energy through the atmosphere to the surface of an object or that point of incidence. So here's what we're talking about. Got a couple of ways of looking at this. First, we'll start off at the top with A. So we're just looking at an energy source, the sun. And we can see that from the very, very low frequency to the very, very high frequency, or the very, very low wavelength to the very, very high wavelength, depending on which direction you want to look at, we can see how much energy comes from the sun. As the graph goes higher, it's producing more energy. As it moves to the right, the wavelength is increasing. And then over here, way out at the end, we see the Earth's energy. Now the Earth's energy is much, much less than the sun's energy. It's also much, much weaker than the sun's energy. Now let's go down to B. This graph shows atmospheric transmittance. And so this graph is a little bit complicated to understand, but it's the same kind of principles. We look across the axis on the bottom, we have the wavelength. And as we move from left to right, the wavelength increases, so the energy decreases, the frequency decreases. The area in this graph that is red is the portion of the energy from the sun that is being blocked or absorbed in the atmosphere. Okay, so on the y-axis we have this transmission of energy. Okay, down at the bottom there's no transmission. At the top it's 100% transmission, and this is relative to the white part of the graph. And so as the majority of the energy is transmitted through the atmosphere, the graph will be white all the way to the top. Whenever it's not, it's red. So as you look across here, I've got two little circles. One says BGR and one says NRG blocked. BGR happens to be the blue and the green and the red spectrum. That is the visible light. And if we look back up to the prior one above, you can see that that is where the majority of the energy exists from the sun, and that is what we can see. And it's also convenient that it is in a giant atmospheric window where there is very little transmission loss. But when you go further over to the right, you can see that there are entire areas where there is nothing that gets through the atmosphere. So let's look at some of these things and what they matter. The next one down, same thing, same scale. And we're going to look at some of these common remote sensing systems. And so the first one we're going to look at is the human eye, which neatly corresponds to the visible light. And then below that we have photography, and you see that it's wider. And the reason is, in photography, we can easily generate film that will collect data in the ultraviolet and in the near infrared. And so we can extend that range to the left and the right of the visible light. Then we have thermal scanners, which pick up from the thermal infrared range up to some point. And then we have multispectral scanners, which literally select or collect everything from the lowest values that our photography could pick up all the way up to the upper end of what the thermal scanners could pick up, and everything in between. And then way over here to the end we have these radar and passive microwave systems. And if you look above, you'll see that there is some loss of transmission, but there's also some parts of that where transmission is very high. So let's take a little bit closer look here. Again, just what I was saying before, visible light, heart of the sun's bulk of their energy. Visible light, atmospheric window where we can see. Other places outside that window might be completely blocked. Next, I want to talk a little bit about spectral reflectance. So what is spectral reflectance? It's the energy of the wavelength reflected from an object divided by the energy of the wavelength of incidence upon the object. Okay? So basically, I zap something with X amount of energy, Y amount of energy comes off of it. I divide the energy coming off by the energy that went on, and I get a percentage, and that is the percent of the energy that was basically reflected. It's not a super complicated concept. Alright, so I've been talking a little bit about this incidence energy and reflected energy, and this is a pretty good illustration of explaining how it works. Now, pay no mind to that fancy little equation up there. We're going to break this down in simple terms. The incident energy is the energy, in this case, from the sun. That energy comes through our atmosphere, and what we're really talking about is the amount of that energy that makes it to the first surface it contacts, the first terrestrial surface. In this case, a lake. Now, when that energy of incidence reaches a surface, it can do one of a handful of things. And whether it's a lake, a glacier, an iceberg, a marshmallow, or a mountain, those options are the same. That energy is either transmitted through that surface, it is either absorbed by that surface, or it is reflected from that surface. In other words, if you add up all the energy that bounces off, and all the energy that passes through, and all the energy that becomes absorbed within the object that the incidence is upon, the sum total should be equal to the energy that was placed there in the first place. Alright. So, how can we use that to our advantage? Well, it turns out that percent reflectance is very different based on what things are made of. Now here we have two leaves, or well, we have two trees that we're looking at in a spectral sense. And when we get in that visible range, blues and greens and red, we really can't necessarily see that much difference. Not enough to, from a photo or from some remotely sensed image, figure out what's what. But an interesting thing happens as we move past the red and into the near infrared. It turns out the composition of the leaves of a maple tree versus the composition of the needles of a pine tree are sufficiently different so that the amount of energy, the percent reflectance, the amount of the total energy that gets bounced off is very different. There is more energy reflected, a greater percentage, from the maple leaf than what is from the pine needle. And so you get a very different signature. And so what does that tell us? That tells us that in the near infrared, one values will be much higher than the other. Here we have an image that does something that we like to call, it's a false color infrared. Well, actually this is a black and white. This is a true infrared image. The one on the top is true color and the bottom is infrared. And so in infrared, what we do is basically we replace the traditional red band, the one that combined with the blue and the green equals this color that you see in the grayscale image above. But when we replace it with the near infrared, the different types of trees show up dramatically different. And some of them look much darker and others look much lighter. Darker would mean that it is absorbing more. Lighter would mean it's reflecting more. Reflecting would be the deciduous trees, the maples. Absorbing would be the needles, the coniferous trees, the pines. We use this information to develop something we call spectral signatures. So a signature implies a unique spectral relationship, just like your signature, that in theory no one else could duplicate. And the idea is that if we measure these different spectral parameters, we can find this unique signature for things. So when we look at biochemical signatures like minerals or the amount of nitrogen in a plant, we can use hyperspectral data to tease that out. However, there are sources of variability that we have to deal with. Number one, these spectra that we're looking at, they're not always unique. There might be a whole lot of things that look dark red in a certain frequency. The other problem is the illumination from the sun is not consistent. And the other thing is there's natural variation within the composition. Not every maple tree is exactly like every other maple tree. And to top that off, if that wasn't enough of a problem, this is all raster based, and so our information is only as fine as the detail pixels that we have. And so some of those pixels are going to be at the boundary of, say, the forest where there's one kind of thing and something else, or it might be that there's a mix of two different kind of trees together, ultimately leading to something called a mixed pixel, where that individual pixel is not a single thing in it that we're looking at. In fact, there's multiple things, and so we get some variability there that we were not anticipating, and then just general noise that could be coming from any number of things. So here we're going to look at a couple other things, these ideas of spectral signatures. Simple graphs, wavelength, left to right, low to high. Left side on the y-axis we have the reflectance, in other words the percent of energy that is reflected. And we're going to look at some different things for these. And so If you're trying to separate soil from vegetation, or if you're trying to separate clouds from snow, dead plants from living plants, if you're trying to figure out what plants have water stress and what plants have nutrient deficiencies, this is some of the things that you can do. So let's take a look at the first one. We have soil, grass, and dry grass. Now right off the top of your head, you'll notice that once you get above a certain wavelength, the soil tends to reflect more of the energy than the green grass. And at the other end of the spectrum, the soil tends to reflect more again, but in between there's an area, and obviously it's in the visible range where the green color exists, that reflects more than what the drab color of the soil does. But yet when we take the grass and we dry it out, it follows a pattern that is a little more like the soil. And so what is that an indication of? It could be an indication that the real big difference here is the amount of moisture in these things, and that green grass has more active chlorophyll and moisture than dry grass, and the dry grass less that moisture appears more like soil. Next we'll go down and look at a couple other things. If you're trying to figure out what's concrete and what's asphalt versus what's sand, you can see that they have very different spectral signatures, and so you would look for a spot where you could tell them apart. You wouldn't want to look for a frequency like, for example, if you follow that pure gypsum and sand line going from left to right to where it contacts the asphalt line. That would be a bad spot, because at that point you couldn't tell between the two. Now you could still identify the concrete, but not that. But if you move just a bit over to the right or move a little bit back to the left, you have distinctly different ranges of values there for the asphalt, the concrete, and the sand. Talked about clouds and snow. You're probably thinking, how can we tell them apart? They're all just water. One's water vapor and one's frozen water. Well, that actually makes a difference. If you look down there at the amount of energy that's reflected from water, it's not very much. And the reason is it transmits a lot and it absorbs a lot, but it doesn't reflect much. But the moment you make it in water vapor, like clouds, it begins to reflect a significant amount. Partially because of like non-selective scattering. The water molecules are larger than the wavelengths of the light, so the light hits them and it just goes nuts. But snow, it's even more opaque and crystalline. And so what do we get with the snow as opposed to the clouds? We get almost 100% reflectance, and that's why snow is white. But interestingly enough, there are points further to the right in the spectrum where clouds will be looking at about a 60% reflectance and snow will be less than 20, and that is a distinctly different value from one another, and that makes it a wonderful place to try to tell them apart. So what are some of these spectral reflectances of features on Earth that we need to look for? Chlorophyll at 0.45 and 0.67. Near infrared is useful for identifying changes in plant species. There are these water absorption bands, or certain frequency where water absorbs a lot of stuff. 1.4, 1.9, and 2.7. Snow absorbs more in the mid-infrared than clouds. Above 1.4 you can tell if it's snow or if it's clouds. So here's what we're looking at. Reflectance again, wavelength, dissolved organic carbon in water samples versus clear water versus water that's got a lot of algae and things like that growing in it, so it would have a lot of chlorophyll. Again, very unique signatures that you could at different places figure out how one is different from another. So what are some of the atmospheric influences that affect these patterns? Well, sunlight's not always the same. It has this unspecified path length. Are we talking about things that are reflecting back up? How long is that path length? All this goes into changing what the sensor actually picks up. So when we look at the radiance from the satellite versus the surface, it's not always the same. And there's geometric influences as well. Certain angles things go good. Sometimes your reflecting surface isn't perfect, and so it sends it off in multiple directions, and sometimes it diffuses it a lot, and sometimes pretty much everywhere. You can also have areas that are in shadow and areas that are not in shadow. That can contribute to it a great deal. So there's lots of little things that can go into it that can cause these values to be different, because it makes the light pass through more atmosphere. This is similar to what we looked at earlier. Here we have the same kind of a graph wavelength, and then we have the percent reflectance, and then on the right we have atmospheric transmission. Okay, and so we're looking, the black line is dealing with the reflectance. The gray blob coming down from above has to do with transmission. Okay, and so at some spots it'll show 100% transmission, and no, I guess it's the white is the 100% transmission. Yeah. So the areas that's gray is the not transmission section. So if we look at some of these factors, like the pigments in the leaves, chlorophyll, A and B, beta carotene, those sorts of things, they come to a certain range that all fall in the visible light spectrum. Above that, there's this scattering that has to do with the leaf structure and parts of it called the spongy mesophyll. And in that area, we have a somewhat higher reflectance. We also have some atmospheric absorption. As we move on over, the leaf water content becomes important. And you see that these atmospheric water bands we see at 1.4 was it looks like 1.9 and 2.6. Those are areas where nothing gets through. So when we think of vegetation, reflectance, absorbance, and transmittance, we can sort of graph out how something looks. We can use this information with our vegetation and compare it to just water absorption, and we can use it to figure out a lot of interesting things. One of those things is moisture stress. Here we have a plant, Magnolia grandiflora. That's a magnolia tree, in case you're wondering. And what we're looking at here is the spectral signature of it relative to, and this is important, relative water content. So when the leaf vegetation is fully saturated with water, you get the solid line, the 100% line. The area that's below it is indicated as the gray part of this map. As the water content drops to 75%, 50%, 25%, and 5%, you can see how in some parts, in some places, these patterns change a lot. And so if we're measuring in those wavelengths, we can, for example, pick a wavelength relative to a particular moisture absorption band and literally tell how much moisture is in the leaf relative to that value. And from that, we can then determine how at stress that plant is relative to moisture. We can do the same kind of thing and try to figure out different tree species. Black spruce versus aspen. That's what we're seeing on the right. Maples versus pine trees. That's what we're seeing on the left. The pattern on the left is reflected in the right in this false color infrared. going to talk just a little bit about soil reflectance. First thing, remote sensing data is not really that useful for diagnostic efforts in terms of soil types. Soil in general is drab in color. Over time, it accumulates organic matter, and it may or may not turn orange or yellow or red relative to the iron content. It can also get purples from manganese, uh, lots of different things. And so the colors that we can detect are not super good for identifying soil types. They can be helpful for some things. And somewhere around 2.2 micrometers is this clay band, and that is a spot where the crystalline structures of clays have a response in the electromagnetic spectrum that's different than other things. So here's what we're talking about. We've got this piece of soil, and we're looking at it across the different wavelengths, and we get up there around 2.2, and there's a tiny little bump. Now, if you look there below 2, there's a great big dip. And you look over at 2.5 and it's tailing back off. But in between, and that little rise, you see that tiny little spot in the bottom one that gets bigger and more pronounced as you go up. That is the clay band. The size of that spot can tell you a good bit. The main thing is it tell you that you got some clay-sized particles there. The other thing we can get from this is that by looking at other wavelengths, we can get a pretty good idea of the moisture content, how moisture dry that soil is. In this example, we're looking at everything from 8% down to 20, and very significant changes in values relative to those changes in moisture. There's the water absorption bands. There's that hydroxyl clay absorption band that I was talking about. Soil organic matter is another primary driver of color in soils, and what we're going to look at here is how the reflectance changes relative to increases in organic matter. As the soil organic matter content goes up by a percentage or more, the percent reflectance drops. What happens is the organic matter absorbs the electromagnetic spectrum better, more of it, and so you go from having little organic matter and reflecting everything or a significant amount of things up to I've got 4 or 5% to now I only reflect maybe 25% of my energy, and that means the soil is going to be absorbing a higher percent, and when you absorb all or most of that energy, the color you're going to appear to be is black. And that is what happens with the soil organic matter. As the organic matter content increases, the soils darken. And the reason they darken is they don't reflect as much light. Now there's other things, not just the organic matter that we look at. There's iron oxides. So here we've got some samples that we've looked at that have no treatment, and then they have the iron removed, and then we have a treatment where the organic matter is removed, and we've got a couple of different soils there, and you can see how making those treatments change some of the stuff, but other things doesn't change much at all. You still get out there around 2.2, and you still have that little bump for the clays, but it does change some of the other things when you do those processes. Here's another example. We have this loam soil with no iron oxides, and then we have one with iron oxides. And what do we get? We get a band, a little spot there, a little dip, where we have this iron oxide absorption band. And then we have this other part where we have an increase in the red reflectance. The soils that have iron oxides are more red, so you would expect that they would have a higher percent reflectance in the red wavelength because that's what we see. Texture wise, textures just has to do with the particle sizes, clay being the smallest, silt being the middle, sand being the largest. And in this example you can see how sandy soils have a lower and different profile than silty soils. So what does all that mean? Soils are basically drab. Organic matter lowers reflectance, especially in the visible range. Water lowers the overall reflectance. Iron oxides boost the red, and they also reduce the near infrared in certain areas. Clay absorption features occur around 2.2, and finer texture soils have a brighter reflectance. That means the more clays relative to the amount of sands and silts, the brighter the reflectance values. In other words, the less of the lower dull colors and the more brighter ones you'll see. So now that we've sort of got some of that stuff out of the way, another part of this process is something called reference data. Reference data can be a lot of things. It can be something we ground truth, where we go out and say, yeah, this looked like this, sure enough it is. But it's not always on the ground. It might be something we're looking at up in the air, like smoke or clouds or whatever. We can also utilize our GPS instrumentations when we're collecting some of this data, and we need to make sure that they're reading properly as well, so that we can reference back to where the information comes from. Um, uh, Typically we check it at a better or higher resolution um, than what we're going to try to explain, and that helps us with remote sensing data. If we know that we've got reference data that's better than the remote sense data we're using, it's helpful. As far as the GPS systems, we're going to go over this a lot more detailed later, but for now let's just stick with some of the basics. Our system of GPS here in the US has 24 satellites. The Russian system of GLONASS has 24. There's a system called COMPAS that they're constructing. They've probably finished it till now. It has 30. All these systems are really GNSSs, which is a Global Navigation Satellite System. Galileo is another one. I can't remember which. Galileo or COMPAS, one of the two, is a European Union project. So what causes errors with these things? Interferences like the atmosphere, the quality of the clock. How do we fix and correct for these? We use augmentation systems, like a differential correction system, and things like wide area augmentation systems that provide us other means of correcting for the given distortions on a given day, and ultimately that helps us to more accurately collect GPS data.